Atomic absorption spectroscopy is a quantitative method of analysis of any kind of sample that is applicable to many metals and few non-metals. Atomic absorption spectroscopy is a spectroanalytical procedure for the quantitative determination of chemical elements using the absorption of light by free atoms in a gaseous state. In analytical chemistry, this technique is used for determining the concentration of analyte in a sample to be analyzed. AAS can be used to determine over 70 different elements in solution or directly in a solid sample used in pharmacology, biophysics, and toxicology research.
The quantity of interest in atomic absorption measurements is the amount of light at the resonant wavelength, which is absorbed as the light passes through a cloud of atoms. As the number of atoms in the light path increases, the amount of light absorbed increases in a predictable way. By measuring the amount of the light absorbed, a quantitative demonstration of the amount of nanolight element present can be made. The atom cloud required for atomic absorption measurements is produced by supplying enough thermal energy to the sample to dissociate the chemical compounds in free atoms, aspirating a solution of the sample into a flame aligned in the light beam serves this purpose.
As an example, atomic absorption spectroscopy has served the forensic community for 40 years and continues to work effectively for such diverse applications as gunshot powder residue analysis and toxicological examination in suspected heavy metal poisoning cases. These and other traditional forensic applications have utilized other forms of spectrochemical analysis, such as neutron activation. The advantage of various forms of atomic spectroscopy over the other method lies in the practical consideration and accessibility and cost, as much as in sampling requirements and the detection limits. From well-established AA methods to the increasing number of forensic applications being developed for laser inductively coupled plasma mass spectrometry. Atomic spectroscopy proved itself to be compelling and evolving tool in the investigation of forensic evidences.
The technique is increasingly being used in the food and beverage industry to ensure compliance with stringent global legislation. Combining flame, furnace, and vapor techniques, atomic absorption facilitates the analysis of a large number of toxic trace elements across a widely analytical range from parts per million down to subparts per billion. The technique can achieve the requirement low detection limits and it offers a maximum ease of use, sensitivity, and accuracy. These characteristics makes AA an ideal choice for the analysis of trace elements for some foods.
Every crystalline substance gives a pattern. The same substance always gives the same pattern, and in a mixture of substances, each produces its pattern independently of the others. About 95% of all materials can be described as a crystalline, and when X-rays interact with a crystalline substance, one gets a diffraction pattern. The X-ray diffraction pattern of a pure substance is therefore like a fingerprint of a substance. The powder diffraction method is thus ideally suited for characterization and identification of polycrystalline phases.
X-ray diffraction is most widely used for the identification of unknown crystalline materials, for example, minerals and inorganic compounds. Determination of unknown solids is critical to studies in geology, environmental science, material science, engineering, and biology. Other applications include characterization of crystalline materials, identification of fine-grained minerals such as clays and mixed-layer clays that are difficult to determine optically, determine of unit cell dimensions, measurement of sample purity. With specialized techniques, XRD can be used to determine crystal structures using Rödtfeld refinement, determine of modal amounts of minerals, characterize thin film samples, by determining lattice mismatch between film and substrate and to inferring stress and strain, determining dislocation, density, and quality of the film by rocking curve measurements, measuring superlattice in multi-layered epitaxial structures, determining the thickness, roughness, and density of the film, using glancing incidence X-ray reflectivity measurements, make textural measurements such as the orientation of grains in a polycrystalline sample.
Strengths and limitations of X-ray powder diffraction. What are its strengths? Powerful and rapid technique for identification of an unknown. In most cases, it provides an unambiguous mineral determination. Minimal sample preparation is required. XRD units are widely available and data interpretation is relatively straightforward.
Limitations. Homogeneous and single-phase material is best for identification of an unknown. Must have access to a standard reference file of inorganic compounds, and it requires tens of a gram of material which must be ground into a powder. For mixed materials, detection limit is 2% of sample, and for unit cell determinations, indexing of patterns for non-isometric crystal system is complicated. Peak overlay may occur in percent for high-angle reflections.
Action.
As the number.
Suggestor na yun. Action.
Atomic absorption
Smile.
I have
Action.
I have an apple.
Sila yung na yun, bucha.
It provides fuck you! Si Wog. Minimal sample per Minimal sample.
Ng science,
Per pineapple.
Mostly.
Tortilla, mano, yes. Tortilla, mano, yes.
Dadaling ko na ito sila.
ayun na, uwi na nila ako.
Ne pregunte. Ne pregunte.
Game.
Tara, game.
Apple pineapple.
Namiss ko tuloy sa cellphone ko.
Apple.
Stare contest.
Per pineapple. Apple pen.
Ano nga, pala yun. Maliit ka pa, boy.